Hello. So topic for today's discussion is uh, about the correlation coefficient. So what does correlation coefficient actually signifies? So let's start with it. Okay. We know that from the very beginning that correlation coefficient, that is a simple Pearson correlation coefficient, is given by covariance between any two random variable xy is nothing but equal to covariance of that random variable xy divided by standard deviation of that random variable x and standard deviation of that random variable y. So what does this correlation coefficient actually do? It measures the strength of linear association. It measures the strength of linear association between two random variables. Okay. So if we have two random variables, say x and y, and if they are perfectly means related in a linear fashion, that is suppose y can be written as a plus bx. Okay. Means there is a perfect linear relationship between y and x, so we can say that the correlation coefficient for them is given by +1. Okay. And in the same manner, if this is about positively correlated, and if y and x are negatively correlated, then their relationship is given by this. So let's show how this relationship can be proved. So we know that correlation coefficient is given by covariance of xy times standard deviation of x times standard deviation of y. So these sigma x square and sigma y square are nothing but the variance of x and variance of y. So taking under root of both of them will give us standard deviation. So actual definition is covariance of x comma y divided by sigma x times sigma y. Okay. So what I will show it for y is equal to a plus bx. Same thing can be done for y is equal to a minus bx. Okay, in the similar fashion. So what we will start with is, so we will start with the expectation operator. So expectation of y can be written as expectation of a plus bx, and suppose expectation of x is nothing but x bar. Okay, that is x bar is the mean for of a random variable x. Okay, then this can be written as expectation of a plus bx, that is, we know from the linearity property of expectation operator, that is expectation of any constant is given by constant itself, and expectation of p plus x is nothing but p times expectation of x, and it is nothing but b x bar. Okay, so this is about expectation. Now similar thing with the variance. So variance of x, let us assume it is sigma x square. Now variance of y can be written as variance of a plus bx. Okay. Now from the property of the variance, we know that variance of any constant term is equal to 0. So we can first distribute this. So variance of Px. So variance of constant is 0. And the variance of constant time a random variable is nothing but b square times variance of x. And we have assumed variance of x as sigma x square. So it is nothing but bx times sigma x square. So it is nothing but variance of y. So what we have till now is, so we have variance of x, which is sigma x square, variance of y, which is b square times sigma x square. So we have denominator for the correlation expression. Now we will find out a numerator, that is, which is covariance between x and y. So straight away from the definition of covariance, we can write it as x minus x bar times y minus y bar. Okay, so E can be written as, so keeping x minus x bar as it is, and substituting for y is equal to a plus bx. Okay, we have assumed, and y bar we have calculated as a plus bx bar. Okay, so here we can see expectation, that is a plus bx bar. Okay, now we are left with just algebraic manipulations, that is, so a and minus a will get cancelled, so b we will take common, then we can write it as b x minus x bar. Okay, so we know that expectation is a linear operator, so taking the constant out, we can write e as x minus x bar, x minus x bar. Okay, so it is b e x minus x bar whole square. Since from the definition, suppose x is any random variable in, and if we want to define variance for x, so we can write variance of x as expectation of x minus x bar whole square. Okay, so straight away it is giving us b times variance of x, and b times variance of x is nothing but b times sigma x square. Okay, so we have expression for covariance as covariance of x comma y is given by b times sigma x square. So it is when y is equal to a plus bx. And similarly, we have variance of x as sigma x square and variance of y as b square times sigma y square. We have calculated it above. Now, what we will do is we can write correlation coefficient as, that is, rho xy. Okay. Suppose I am denoting correlation coefficient as rho between two variable x and y. So it can be written as covariance of x comma y. I have stated this definition above also, times variance of x ka whole square times, it is nothing but variance of x times variance of y, or in other term, it is covariance xy. So variance of under root variance of x is nothing but standard deviation of x times standard deviation of y. Okay, so we have calculated variance of x, so we will put these values. So covariance of xy is nothing but what we have calculated above. So keep this in mind. So it is nothing but b sigma x square from this. Okay, and under root we have variance of x is sigma x square, and variance of y is b square times. It is variance, not. So it is b square sigma y square, sigma sigma x square, not y square. We have calculated it above. Where it is, yes. Okay. So after solving, what we will get, it is b sigma x square. Similarly, here we have b sigma x square, so it is 1. So as we can see that the correlation coefficient for the two random variable which are linearly associated, perfectly linearly associated, is given by 1. Similarly, if we have what we can say, y is equal to a minus bx, so in the numerator, instead of b sigma x square, we will get minus b sigma x square, and rho xy will become minus 1. Okay. So other than that, if we have some linear relation, non-linear relationship of kind y is equal to a x square, say, between two random variable, for that we have rho xy will be 0. By following the same argument, you can show this result, prove this result. So what point I am trying to convey is, if two variables are linearly associated, perfectly linearly associated, then their correlation coefficient will be either +1 or -1 depending upon their slope. Means either they are moving upward or either they are moving downward. And if two variables are non-linearly related, then talking about this correlation coefficient, that is Pearson correlation coefficient, will not make any sense. But mathematically, you can show that correlation coefficient between the two variables which are not non-linearly related is equal to 0. but this does not make any sense because the correlation coefficient is used only for testing the strength of the linear relationship. Okay, so this thing you have to keep in mind. And if you have any doubt, please feel free to reach out to me in comment section. And thank you.